Hello students, this is Narendra Kumar Dwivedi welcoming you all in my channel Narendra Kumar Dwivedi, the physics lover. So today's session is going to be quite interesting. As you can see, the first topic that we will be covering on the board, dielectrics and electric polarization. So basically, as we have earlier discussed about dielectrics in the previous lecture, that dielectrics are basically the insulators which, when gets placed in between the parallel plate capacitor, they increase the capacitance of that capacitor. This phenomenon was first observed by Michael Faraday, and he said when the insulators are kept in between the parallel plate capacitors, then the capacitance or the capacity of that parallel plate capacitor increases. The factor by which the capacitance increases is known as dielectric constant or electric permittivity. So let's discuss this topic. These dielectrics are basically of two nature, one polar and next non-polar. So here first we will be discussing polar dielectrics. Polar dielectrics. So polar dielectrics are basically those insulating materials in which the centers of gravity of protons, that is positive charges, do not coincide on the center of gravity of electrons, that is negative charges. It means there is permanently existing dipole moment of single molecule of such material. So for example, we can say N2O, H2O, HCl, H3, etc. These are such materials which have got, or whose molecule, single molecule has got permanent electric dipole moment. So the polar molecules have such molecules have permanent dipole moment, permanent dipole moment of the order of 10 powers to minus 30 coulomb meter, and hence called permanent electric dipoles. So this is the order that each molecule of such materials have got in terms of electric dipole moment. So they have permanent electric dipole moment. So here let me just draw the picture how that look like. This is basically your H and this is Cl, having this much separation between center of gravity of H and Cl, that is positive and negative, and this is the electric dipole moment direction here. Now likewise for H2O we can draw, this is oxygen. Now here we have two hydrogen associated with this H H, now O, and this is the direction of dipole moment P. Now, further we can see, in the absence of electric field, external electric field, these molecules are so arranged inside the inside the polar dielectric material that the electric dipole moment of single molecule gets cancelled with the electric dipole moment of next molecule of that specimen. So on the whole, the average electric dipole moment per unit volume of that specimen is always zero in the absence of external electric field. Now, looking here, in the absence of electric field, when E is equal to 0, means no electric field is applied here, so that time the atoms are arranged in such a manner that we have, suppose this is next molecule. So as can be seen, this has got electric dipole moment along this direction, so that gets cancelled with this, and here this has got this downward electric dipole moment, so this will get cancelled with this vertically upward acting electric dipole moment of this molecule. So the arrangement inside the molecule, inside this specimen of polar dielectric is such that the electric dipole moment of every molecule is cancelled with the next molecule within the slab. Hence, the electric dipole moment, the average electric dipole moment per unit volume of dielectric is 0. Now, what happens when these materials or this polar dielectric is applied or is kept in an external electric field? So that external electric field tries to just rotate, tries to align these randomly ordered electric dipole moments of every molecule of that specimen, so that there is a non-zero dielectric moment of the slab or the material itself. Now this alignment is not complete due to the thermal vibration, thermal agitation. That thermal agitation or thermal vibration of these molecules hinders the complete rearrangement of these electric dipole moments in the direction of external electric field. So that complete electric dipole moment arrangement or alignment of every molecule of the specimen can be better obtained by lowering the temperature or working at lower temperature and increasing the strength of applied electric field. So let's see how the specimen look like when it is kept in an external electric field. So here on the next diagram, the electric field is non-zero, that means it exists along this direction, left to right. And here, suppose we have a molecular electric dipole along the direction. Now here this is along this, and here say this is along this, and here it is along this. So as you can see, this electric dipole moment is just along this electric field, external electric field. This is at slanting position to this electric field, this is also slanting upward position to this external electric field, and this electric dipole moment is completely along the direction of electric field. So this way the arrangement or the alignment of molecular electric dipole moments takes place when the external electric field is applied, and this arrangement, this alignment can be better obtained, can be completely obtained by lowering the external environment temperature, surrounding temperature, and increasing the strength of this applied electric field. One more thing we can add to this: the polar molecules exhibit a special characteristic in terms of dipole moment when they are exposed to some external mechanical stress. So when the mechanical stress is applied to such materials, they show the change in electric dipole moment, and this effect is called piezoelectricity. This effect is called piezoelectricity. So it is the phenomenon of the specimen of the crystal of polar dielectric in which it shows certain changes in electric dipole moment when applied with external mechanical stress. So that phenomena is called piezoelectricity. Okay students, so let's move on with the next type of dielectric, that is non-polar dielectric. So non-polar dielectrics basically are those insulating materials in which the centers of gravity of protons, that is positive charges, coincide with the center of gravity of electrons, that is negative charges. It clearly indicates that there is no electric dipole moment existing from the prior position or from the previous position. In the normal state, such material, non-polar dielectric material, do not have any electric dipole moment, talking in terms of individual molecule. So no molecule of such material have got previously existing, permanently existing electric dipole moment in the normal state, and the specimen as a whole also does not have any previously existing electric dipole moment. So for example, like N2, O2, these are O2, N2, H2, CO2, etc. are few examples of such non-polar dielectrics. Here, when the normal state is there, that means when no external electric field is applied to this specimen. So how does this look like? Let me draw this. Electric field is equal to external electric field is 0. So here the centers of gravity of positive and negative charges that coincide of every single molecule within the specimen of such material. So this is the picture. Here no molecule has got electric dipole moment, as the separation between positive and negative poles or charges is 0. They coincide over each other, and hence the specimen has got no electric dipole moment. Now what happens, let's see, when this specimen is exposed to an external electric field. So that externally existing electric field tries to separate the centers of gravity of positive and negative charges so that every individual molecule of such material has got electric dipole moment non-zero. So this separation is dependent on the strength of external electric field, and this separation of center of gravity under the effect of externally applied electric field is called the polarization of non-polar dielectrics. Now the separation continues till the externally applied force on these charges, these centers of gravity of charges, gets balanced by the internal forces between those two charges. So let's see how this works. When such specimen is exposed to an external electric field which is non-zero, that means the electric field is there acting, and now this electric field tries to pull the center of gravity of positive charge along its own direction and the center of gravity of negative charge opposite to the direction of the external electric field. So this way positive and negative charges start separating, and we have a picture seen within the specimen as is being drawn on the board. So this way the specimen look like negative, positive. Here also we have this 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 negative, positive. So this way the net electric dipole moment of molecule as well as this specimen as a whole is seen along the direction of external electric field, and this process of separation of centers of gravity of positive and negative charges is called the polarization. Now, as can be seen, the polarization is directly proportional to the external applied electric field. Means as stronger the external field applied is, the so as the strength, or so as the what should I say, polarization process, strength of polarization process within the slab. So here we can further write that vector P is just equals to epsilon naught alpha times vector E, where this alpha is called constant of proportionality and this is called the polarizability of non-polar dielectrics. So here alpha is the atomic polarizability, polarizability. Okay, now the SI unit of this unit of alpha is the unit of volume of that specimen. So we can write is cubic meter, whose value its value ranges from 10 past 2 minus 29 coulomb meter sorry, 10 past 2 minus 29 cubic meter to 10 past 2 minus 30 cubic meter. So this is the range of this polarizability constant, alpha atomic polarizability is. Okay students, so let's see now how the polarization process within the dielectric takes place. So let's see the next topic, subtopic I must say of this topic, that's polarization of dielectric slab. So let me just draw a diagram. Suppose we have a uniform electric field getting obtained with the help of a parallel plate capacitor charged with positive and negative. So this is the second plate of capacitor charged negatively. Now here the external electric field is from left to right. Now let me just place the dielectric slab, especially non-polar in nature, here in between this gap of parallel plate capacitor. Now this external electric field tries to separate the centers of gravity of positive and negative charges and tries to induce the electric dipole moment of within the single atom, within the single molecule of that specimen. So let's see. Here actually this is the imaginary line. Here also I am drawing this imaginary line. So here the separation would look like this. Here it is negative, positive, and here also it is negative, positive. Here also it is negative, positive. Here also it is negative, positive, negative, positive. So here also I must mention negative, positive, negative, positive, negative, positive, negative, positive, negative, positive. Now within this I must also draw the same picture like this, like this, like this, negative, positive, 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 negative, positive. Let me draw this with shade because this reason will be of our interest. Here we will be discussing so this way the molecular dipole moments are aligned under the effect of this electric field. The alignment of permanent or induced dipole moments along the direction of external electric field is called the polarization. Now as can be seen, the positive end of this specimen, dielectric specimen, close to this negatively charged plate, and this negative end to the left of this specimen close to positively charged plate remains uncancelled, and here within this middle region every charges will get balanced by, will get neutralized by the next neighboring charge. So this way the specimen of this dielectric material within this parallel plate capacitor is said to be polarized, and these charges, positive induced charges to the right face and negative induced charges to the left face, are said to be the induced charges or bound charges, as they are not free, they are bound with their next neighboring positive and negative charges. So these are called bound charges, and hence these are also called induced charges. As can be seen, these induced charges remain there so long as there is electric field. As we just take this specimen away from this or take out of this electric field, so these induced charges disappear. So for this reason they are also said to be fictitious charges. The field produced by this surface charges try to oppose the externally applied electric field. That means here the induced electric field due to these induced charges will be from right to left, and the externally existing electric field is directed from left to right. So this way this induced electric field tries to oppose the external applied electric field and tries to reduce the strength of this applied electric field. Okay students, so let's move on with next subtopic, that's polarization vector. So polarization vector is basically the vector used to test or check the strength or to what extent the dielectric is polarized, or to what extent the molecular electric dipole moments are induced under the effect of external electric field. So this is measured with the help of this polarization vector. Here for the consideration, let me write this: consider two charge centers of a polarized atom separated by distance delta. Here delta is the distance that we are having, that is there to signify the separation between the centers of charges. Now the magnitude of the dipole moment of the polarized atom is given as P equals to charge into separation between them. So here actually polarization vector can also be defined as the dipole moment induced per unit volume of that specimen. So polarization vector can also be defined like that. Now say if there are n atoms per unit volume of dielectric, then the dipole moment density is, dipole moment density we are just representing it by capital P, and that is equal to n into small p. So here, just placing the value of this p back, we have this n q into delta. Also we have p equals to n alpha epsilon naught e. Okay, now let's have next fifth subtopic, that's relation between P, polarization vector, and surface density of induced charges. So polarization is basically the relative displacement of positive and negative charges of non-polar dielectric. So here, suppose let plus minus Qi be induced surface charges plus minus sigma I surface density of induced charges X be the thickness of slab that is kept within the parallel plate, and A be the area of the slab. Okay, with these considerations we'll be proceeding further. Now dipole moment of slab, we can write induced charge into separation, so Qi into X. Now we can write volume to have the density, or to have, I must say, polarization, dipole moment per unit volume. So volume of slab equal to area times separation. Now polarization we can talk of. Polarization P equal to dipole moment induced per unit volume. Now this will get cancelled, and this is what? Sigma I, induced surface charge density Qi by A. Now in vector form you can write sigma I equals to vector P dot vector n cap, where this n cap is unit normal vector to the surface. Okay, so this way we can. Okay students, so let's have next topic with us, that's electric susceptibility of dielectric. As the polarization process, or the relative separation between centers of gravity of positive and negative charges, is the function of externally applied electric field, means as stronger field is applied, as much as the separation between the centers of gravity of positive and negative charges takes place. So this way we can see the polarization process is proportional to the external applied electric field, or we can write P equals to chi epsilon naught into E, where actually this chi is constant of proportionality and it is the electric susceptibility of that is the electric susceptibility of dielectric. Now here actually this epsilon naught multiplicative factor to right hand side is just only there to make the equation dimensionally correct, and here we write larger the value of this electric susceptibility chi, greater will be the polarization of dielectric in an electric field. So this indicates this chi can also be treated as the measurement of extent of polarization. So if this chi has got larger value, so is the larger polarization, larger amount of polarization seen within the slab when it is placed in an external electric field. So students, with this we end up today's session. I hope you all are enjoying this learning. So do like and subscribe the channel.